Let's do this. So I've been, welcome back folks, I've been trying to get caught up on posting things. So homework 5 I think folks have mostly completed. If not, that should be hopefully done soon. Homework 6 is due this week. Have you guys started that? Right here. This is the week we are. Yes. Happy post-tax day, I guess. 4:15. Once upon a time in college, I waited tables, and sometimes the part of the restaurant would be rented out for a party. And I remember one year I got to work a party on April 15th, tax day, for an accounting firm. Man, did they drink a lot. I cannot say I blame them though, but accountants can party. They'll party like it's tax day. You know, it'll be like a new saying. But anywho, happy post-tax day. Homework 6 due Friday. Any questions on that so far?
So we got a problem on quiz 5 because when we open the icon, it should like have the photo, but it's all like text based, so we cannot see the photo.
Let me see what.
Did you put the model in like a picture?
I put an equation in, and the picture's not rendering.
No, it's all about like text.
That is the HTML code that should render the equation. Okay, so I need to fix that somehow. Yes. Yes, I can do that. Thank you for letting me know. Sorry about that. Yes, so I will fix quiz 5. It is very much like what we did in class last week, so it shouldn't be too complicated.
From left to right, you understand what it says.
Yeah, there's some mistake in the translation. I think there might be a tag missing or something, but that's the HTML code that renders the equation. But yeah, you shouldn't have to work that hard. That was it should just show as a.
I hope I knew it. I hope I knew it half an hour ago.
We'll figure it out. But homework 6 questions. Not yet? That's fine. I'm just asking. If the answer is not yet, that's fine. We've got interactions to finish up today, and then on Thursday we will resume the world of time invariant predictors, which will have a lot of interactions, which is why we're reviewing them. So any other housekeeping things before we dive in? No? Okay. So last week we talked about interactions among quantitative predictors or continuous predictors. This week we're adding in interactions involving categorical predictors. And there are 2 different ways to set up these types of interactions. I want you to know how both of them work so that you can make a choice for yourself as to which is going to be more convenient in a given situation. So we're in lecture 2C, and then example 2C will go with it. Are we ready? Got it? Okay. So, first up here, the 2 ways by which to put grouping variables, what I call categorical predictors, into a model. One way is to do it yourself by creating contrasts. So manually creating contrasts. So if you have G groups, you need G-1 contrasts, such as dummy codes is the easiest way to think about it. They are treated as continuous by the program. So they are 0, 1 variables for which the program will estimate a slope, the effect of a 1-unit change, but you know that it's just, that's the only thing it could be, is the difference between 0 and 1. I like teaching this way first because it corresponds more directly to what the actual linear model is underneath it. And it's also sometimes easier to get interaction contrasts this way. Now that being said, if you have more than one categorical predictor, it may be more convenient to let the program do all of this for you. So the other way of putting this into the model is to let the program do the coding by denoting it as a categorical predictor. So this is the class statement in SAS, it's the by statement in SPSS, it's I dot in Stata, and it's a factor variable in R. That's the idea, where you're denoting it as a grouping variable, a nominal variable, so that the program then makes the contrasts. You have to then know what the program default is in terms of which is the reference group. So for instance, in SPSS and SAS, it's the highest numeric or last alphabetically. In Stata, it's the first. What is it in R? Do you guys know? Factor variables, what's the reference?
Oh, yeah,
Which, is it the highest, the lowest, or something else? If you denote a variable as a factor variable.
And if it's numbers, what is underneath?
Mm-hmm.
I want to say it does in the lowest, but I haven't actually tested it.
See, this would be good to know, because each program has some rule that it's following, right?
I usually try to set them explicitly afterwards.
Yes, and some programs will let you change it from whatever the reference is. This one is more convenient if you have lots of groups, want lots of contrasts, or have a lot of interactions. But it can be confusing then to reconcile different p-values in different parts of the output that correspond to effects being marginal effects or simple effects. So I have an extended example to show you what happens in this case, because this is one of the most frequent consulting questions that I've been asked in the world of interactions. So first method, doing it ourselves. Useful for pedagogical purposes to understand what the programs are doing for you. Also useful from a linear modeling perspective to understand what happens when you put a grouping variable into a model. So you've seen a little bit of this before, but it's been a while, so we'll go over this quickly. Let's say that we have a 4-group variable. This is just a simple regression model, so we're not in longitudinal land for today. We're just in regular cross-sectional, one outcome per person land. So if I have, say, a control group and 3 alternative types of treatment, so I have a 4-group variable that I want to put in the model, even though I'm thinking of one variable as group, which would be called, say, treat group in my data set, to put that treat group predictor into the model requires 3 contrasts. What those contrasts mean is totally up to me, but I know I need 3 of them if there's 4 groups to be differentiated. In this case, what I've chosen to do is to denote the control group as the reference. So in all 3 of the new contrast predictor variables that I'm creating here, control is coded 0. I'm making a new variable D1 where the treatment group gets a 1 and every other group gets a 0. D2, the treatment group 2 gets the 1 and every other group gets the 0. And then last, D3, treatment group 3 gets the 1, every other group gets the 0. So then in terms of reconstituting what the mean for each group is, it would look like the table below, where the mean for the control group is given directly by the intercept, the fixed intercept beta 0. The mean for each other group is given by the intercept plus the contrast that differentiates that group. So there's 3 group differences given directly by D1, D2, and D3. There's 3 more that are implied by the model that are not given unless you know how to ask for them. So the 3 that are missing are the comparisons between the treatment groups, between the non-reference groups. And to get those, how to get those is shown in the last 3 lines of this slide number 4 here. So if we know how to get the mean for each group, we know how to get the mean difference for each group. So for instance, treatment group 1 is given by beta 0 plus beta 1. Treatment group 2 is given by beta 0 plus beta 2. So we can subtract those 2 combinations. The intercepts drop out and we're left with beta 2 minus beta 1. Okay, so stare at this for a moment. See if this makes sense. Where the term that's after the versus is first, and the term that is before the versus is second here as the reference unit. Okay, so we've seen this before. Does this make sense? We're good with this? Do you know how to get these 3 linear combinations? Yeah? Estimate statements or LS means will give them also to you. So I'll show you all of that here in just a second. So here's what the code would look like to accomplish this. So the model in this case, I would have y equals d1, d2, d3. So in this case, treatment group is not going into the model. What's going in instead are my 3 dummy codes. To get an omnibus main effect of whether there are any group differences requires a multivariate wall test. So we saw this, I think, early on. This is the contrast statement. Do you remember this? This is the idea of simultaneously testing whether there are any group differences by testing the effect of D1, D2, and D3, each separated by a comma to delineate the numerator degrees of freedom. So, in other words, what am I doing here? What would you call this model if you encountered it in not this class? What am I doing? This is an ANOVA. And so the omnibus F test for the main effective group that would have 3 degrees of freedoms in the numerator, that's what I'm asking for right here via this contrast. In this case, because group is the only predictor in the model, that omnibus main effect F test is also the test of the R-square. It's the test of the model. To get the mean for each group, I fill in the 0s and 1s, where I'm starting with the intercept everybody gets, and then only the group in question gets the 1 after it. The reference of control versus each one is what's already given by the model. The 3 last statements are the extra ones that I would have to ask for, where D2 minus, or beta 2 minus beta 1 is given by -1 on D1 and 1 on D2. On the last 3 statements here, which is the -1 and which is the 1 is arbitrary. The difference is going to be significant whether it's positive or negative. It's just up to you to keep track of which way it goes based on the original means. When I write these things, I always make it so that the -1 goes with the term listed first and the 1 goes with the term listed second. That works out to the beta 2 minus beta 1, beta 3 minus beta 1, and so forth that's showing up here. Okay. With me so far? Questions? No. All right, interactions. Now what if I wanted to see if the effect of a covariate, such as age, differed as a function of which group you're in? I can do that. But in thinking of a group by age interaction, how many effects is that going to be in this case? And don't say 1. How many effects are implied if I say group by age? 3. Yes. Even though you're thinking of group as one construct, if there's 4 groups, there's 3 group differences, each of which can be multiplied by age. And so we get to the model that looks like this, where we have beta 4 is the main effective age. Given the interactions that follow, this is the effective age specifically for the control group. Beta 5 is how the effective age differs in treatment group 1. Beta 6 is how the effective age differs in treatment group 2. Beta 7 is how the effective age differs in treatment group 3. So then now we have 2 different types of effective group. One is the group difference, what we had before, but now given the interaction terms, this group difference is conditional. For what kind of person am I testing the main effective group? What is it interacting with? Age, yeah. So this is a group difference at 85, at age 85. It would be different somewhere else. So it's the effective group holding age constant, and not just constant, constant at 85. Just as I can test a mean difference due to groups, I can test an age effect difference due to groups. In the same way, I add together the three interaction terms. That's not something you would typically get as part of your ANOVA output. So this model, some people might call it an ANCOVA, analysis of covariance, although traditionally in that model, your covariate is allowed only a main effect without interaction terms. There's no reason not to put the interaction terms in if you need them, though, so I want you to know how to do that. So this model implies that there are 4 different age slopes, one for each possible group. And so the second set here, estimate statements, I'm asking for what the effective age is in each group. The only one that is given to me by default is the first one. You can see that the effective age 1 and everything else is zeroed out. That means it's for the control group. So the logic of these estimate statements is exactly the same as what we did last week. To get what the effective age is, we start with the model and pull out any terms that have to do with age. So when I say age 1 right here, what am I talking about? What do I need 1 of according to my model? Which beta?
B4.
Beta 4. That's what age 1 means. It means, how do I get to the effective age that's predicted by the model? Well, we start with the simple main effective age. That's what it is for the control group. Then we would have to augment it by how the effective age differs in each of the other groups to get to what it is in each group. So in total, if we look at just the first 2 lines here, age slope for control and age slope for treatment 1. The first line gives me the effective age in control. The second line gives me the effective age plus the interaction term for how the effective age differs. So it's a linear combination is what it takes to get to what the effective age is in treatment 1. So there's 3 pieces of information there that we'd want to know for these 2 lines. Is there an effect in the control group? Is there an effect in the other group? Do those effects differ? The model can only give us 2 out of the 3 directly. The third is always implied. Likewise, we can get the age slope for the treatment 2 group, treatment 3 group, and then the difference is down here. So if I want the difference in age slopes between the reference group and each of the other treatments, that's the first 3 lines that are already given to us by the model. The second 3 lines then are implied by the model, and I have to ask for them. So I'm going to give you a philosophy in the example that is going to be different than others that you've heard. Error inflation. One of the things that goes into ANOVA dogma is that if you're testing omnibus main effects, when you do what are called pairwise follow-ups, that's what I'm essentially doing here, you have to worry about error inflation. I don't feel that the 3 statements that you have to ask for are any different in terms of their susceptibility to type 1 error than the 3 that show up by default. So I'm not going to talk about Bonferroni or Chaffee or any other old dead white guy, because to me, every 1 in 20 p-values is suspect. But I'm not going to make a distinction as to how those p-values show up on your output, whether they're default or asked for. I'm just not. That's my philosophy. You can do whatever you want in your lives, but I don't think that some of these are more suspect than others. If I have 4 groups, that implies 6 comparisons. I know that. Some of these comparisons are going to be more interesting to you based on the research hypotheses, but the model implies all of them already. Okay. So how would this look if I didn't do the dummy coding and I let the program do it? Well, that's the other way. Denoting it as categorical by calling it a grouping variable explicitly, factor variable, I dot, etc. Then we have an extra piece of information we can ask for via ls means to get means and mean differences between groups. And the same, it's called margins and stata, it's the same idea. So this is what the same two models would look like. First, just the main effect, and then second, adding the interaction with age, if we let the program do the coding for us. So this is a main effect of group only model. So the difference is that rather than having D1, D2, and D3 as predictors, I put in trait group. But critically, trait group is also on this class statement. Now, what would happen, do you think, if I forgot my class statement? Yeah, it'll put a slope through group 0, 1, 2, 3. Will it spit the output out for you and give you that number? Sure. Does it mean anything? No! So there's a phrase I like to use in terms of beginning statistics learners. Like I say, and I'll tell you this, when I left graduate school, I knew just enough about longitudinal models to be dangerous. You heard that phrase before? Just enough to be dangerous? It means that you know enough to make the program give you numbers. You don't know enough to know when the numbers mean absolutely nothing. So if you think of somebody who's just getting used to running these models, they might put treatment group in the model, but without putting it on the class statement, you're going to get a slope that gives you the difference between 1 and 2 and 2 and 3 and 3 and 4. But that doesn't mean anything. So on the class statement, that's the critical thing here. When you do that, all of this stuff on this slide comes out by default if you add this one line of code, ls means. So this is why it can be much more convenient to let the program do the coding for you, because then it understands what you're trying to do. So behind the scenes, what ls means is doing for you is first giving you the model predicted mean per group. So that's the first 4 lines here. If I wanted to write the code manually to do what ls means is doing, each group, the treatment group variable has 4 values after it, because I have to use a combination of zeros and ones to indicate for which group I want this predicted value. So it's 1 when it's turned on for that group and 0 when it's turned off. To get group differences, all of them, all 6 of them are given to you by diff equals all. Alternatively, if I wanted to ask for them, then that's the combination of -1 and 1. So the zeros and ones in a given line have to sum to 0 in order for the contrast to work. Things that are zeroed are not involved in the contrast. So -1 versus 1 gives me a comparison of the control group versus the first treatment group, and so on. The same omnibus main effect of group that used to be just the 3 dummy codes each with a 1 would look like this. 3 contrasts. I listed the first 3, but it actually doesn't matter what you list. If you list any 3 of the 6 implied contrasts, you will get the same F value for the main effective group. I'll say that again. The main effective group is 3 degrees of freedom. You can ask for it by referencing any 3 of the 6 possible pairwise comparisons. That's all it takes to get the right F value, because the other 3 are linear combinations. And that's why I don't think that the first 3 are different in terms of their susceptibility to type 1 error than the last 3 or any other combination. Sure.
So in SAS, I think they only recognize like the variables as categorical.
Yes, you can only use variables on the class statement in
So
ls.
what if I have the continuous variable as well, and I want to get the group means like centered at the like here in age 85, do I have to code like estimate?
Yes. That's the next slide.
Okay.
Yes. Yes.
So there's no way to just get the results out from the LS means?
There is, but right now age is not in the model.
Okay.
So the model implies the same group difference or group means regardless of age. In the next model, I'm adding age and its interaction. And to answer your question, you add this at.
Oh,
And so that gives you the group means and their differences specifically at these levels of the covariate.
okay. Yeah, I think one of the homework questions, since homework 5, I tried to tell SAS to give me the means, but it doesn't, because it says like the arrow, the variables I put has to be like in the class statement.
Mm-hmm.
Okay.
Yeah, like, so if I asked you for the predicted mean at time 3 or something from a linear model, yeah, you have to figure out what the estimate statement is to get that. It's not a mean per se.
Okay.
In the same way that it's looking to marginalize across groups. But yeah, so in this case, what she was asking about is how do I condition on a continuous variable? So this slide then gives me group differences at particular ages. The other piece of this that you would have to ask for then is what is the age slope per group? That isn't given to you by LS means. So anything involving a continuous variables effect, you have to code for which group you want the effect, and this is how you would do it. So to get the age slope for any group, it starts off with age, which is the beta 4, and then it turns on for which group you want the age slope. To get the age slope differences, like if I wanted treatment control versus treatment 1, I would literally take this whole line right here, the middle line, second line, and subtract the first line to get what is control versus treatment 1. And if you do that subtraction of those lines, you end up with this contrast right here. The main effective age drops, and you get -1 for control and 1 for treatment. And that gives you the age slope difference. So if I wanted to explain an interaction of group by age, I could do it 2 different ways. One way is given by this LS means up here. I could talk about how the group difference changes as a function of how old you are. Like the groups are closer together in older people, or the groups are further apart in older people. I could talk about it that way, where age is the moderator. The other way I could talk about it is where age is the thing I care about and group is the moderator. And so that would lend itself down here. The effective age is not significant in the control group, for example, whereas it is significant in the treatment group. It's significantly stronger in the treatment group than the control group. That treats group as the moderator instead. Either way, if you wanted to lump groups together and not just do pairwise contrasts, this coding scheme allows you the option to do so. So for instance, if you look at the bottom here, the last 2 lines are an example of a contrast that's not pairwise. So for instance, if you want the control group versus any kind of treatment, and you want to lump the 3 kinds of treatment together to answer that question, the mean age slope across treatment groups would be given by allowing a 1 in each place for the groups, and then divisor equals 3. So functionally speaking, what you're doing is 0.33, 0.33, 0.33. Repeating with the bar across the top, right? Same thing with the bottom one. If I want to contrast whether the age slope is different in the control group versus the mean of the treatment groups, that's a -3, and then 1, 1, 1. So it still sums to 0. The divisor tells you how to make it turn into the 0, 1 coding that we're used to. Okay. With me? Okay. Now, what if I told you that different parts of your output would give you different answers to the same question? Exactly, that look. Kofung's like, where? Because this has happened, and I will show you how this happens. Let's say I have a situation like this. I have a dichotomous variable, such as gender, that I've coded 0, 1, and I have treatment group, which is my same 4-group variable. I have two options for how to tell the program to handle this gender variable. I can leave it as continuous, or I can let it think that it's another grouping variable. When it provides me with the default type 3 sums of squares tests for the marginal main effects, what they mean is going to depend on which coding scheme that I've selected. So if I am using sex as continuous, then the marginal main effective treatment group that shows up is conditional on sex equals 0. If I put sex on the class statement instead, the marginal main effective treatment group that shows up is marginalized across the genders. So you'll have one section of your output potentially that gives you the main effective group, and it will be conditional on one age. And you'll have another, or gender, excuse me, in this example, and then you'll have another section of your output that gives you the main effective group marginally across gender. And those aren't going to be the same answer. So you can have literally what looks like the same term with two different sets of results next to it. So I want to prepare you for that and make sure that you know what you're looking at. So that leads me to say that the stuff that ANOVA spits out for you by default is sometimes completely worthless. I wish I had learned how to ask for more useful information sooner, and so that's what I want to teach you guys how to do. So let's see an example. Example 2C. So I have my renouncing ANOVA dogma thing here. I'm not going to make a distinction between pairwise follow-ups and planned contrast. Do you know what the difference is between those two terms? One gets you yelled at and one doesn't. Planned comparisons, cool. Post hoc follow-ups, bad. I'm not going to play that game. So same data set we've been working with. Last time we looked at age, grip strength, and gender interactions. Now we're going to move into the dementia group by gender world. So starting with what in Chapter 2 is equation 2.13, adding an interaction of sex by dementia group. So it's actually beta 7 and beta 8 here are the two new terms of interest. So this is the version of the model in which I am doing the coding myself. So I am treating everything as continuous because I have manually created dummy codes. So just to remind you the coding scheme here, gender, men are 0, women are 1. I have two variables that differentiate my 3 dementia groups. N stands for none, that's my reference. The first contrast, dem and F, stands for none versus people who are eventually going to get dementia in the future. That's what F stands for. And the second contrast is none versus current, people who already have it. So as you can imagine, people who already have it are doing worse, the worst, and then followed by people who are eventually going to get it, followed by people who don't have it and won't have it. So people who don't have it and won't have it are the reference group. Here are the means that we're going to be analyzing. So these means are holding constant age at 85 and grip strength at 9. The model does not have interactions of dementia group or gender with age and grip, so those group differences would be irrelevant with respect to age and grip, but the means themselves are conditional. So these are what's known as adjusted means in ANCOVA language, or conditional means, but it's the mean differences between groups that are unconditional in this case, other than dementia and gender here. So these are the things that we're looking at. So in ANOVA parlance, when you're inside the table here, these are what's known as cell means. Have you heard that term before? or I'll call them simple means sometimes, or simple mean differences. They are specific to one group. So for instance, 29 versus 26 is the gender difference in the none group. So those are cell or simple. Alternatively, if I'm talking about marginalizing across groups, the marginal mean difference for gender, this 23 versus 17, is marginalizing across my 3 dementia groups. Likewise, 27 versus 21 versus 11 is the dementia group means marginalizing across gender. So the difference, the key to understanding the output is trying to figure out, are you out here in the margins in terms of the means being tested, or are you inside in the cells? That's the difference. In this coding scheme in which I have created all the dummy codes myself, I am staying inside in these cells exclusively, which I would argue is more interesting and useful than marginalizing over 2 different kinds of people or 3 different kinds of people. So here are the 2 new interaction terms in my model. Here is how you would ask for the overall test of the model. So in regression terms, this would give you the F-test for whether your R-square is significant. It is asking for 1 of each of the possible betas in the model, separated by commas to indicate the numerator degrees of freedom. So it's like, on average, do these terms account for variance? This 2 degree of freedom term right here is the test of whether there is any interaction anywhere between gender and dementia. It only takes 2 to replicate all the patterns of differences in these 6 numbers. Now, getting everything that I would want to know. First set here, cell means. Predicted intercepts holding age 80 at 85 and gender or group strength at 9. They all start with intercept. So whenever you're asking for a cell mean, a predicted outcome, a conditional outcome, an expected outcome, all of those words mean the same thing in this context. They start with an intercept. And then all the main effects and all the interactions for those variables that you're not holding constant to some value have to be included. And so these are just zeros and ones, turning each of the respective terms on and off. Stare at that for a minute. See if that makes sense. Okay, with me? So that is how I got these 6 numbers. Next, simple effects. Going back up to the table, I can ask, is there a gender difference in the none group? Is there a gender difference in the future group? Is there a gender difference in current? I can also go the other way and ask for each possible dementia group difference within each gender. Those are what's known as simple main effects or conditional main effects. And the way that you can get them is to literally take the means that you figured out in the first set and subtract the lines of syntax. To do it in the way that we were doing it last week, it's to start with whatever the term is that you're interested in estimating. So the first part of the sentence here, sex difference, that's what we want, right? So at a minimum, back up to my equation here, what do I need? If I'm estimating sex difference for ... What do I need out of here? Do I need intercept? If I want sex difference ... do I need age? Do I need grip? Nope. Do I need sex difference? At a minimum, I need this, right? Because this is going to be the sex difference for the reference group for dementia. Do I need the main effect of dementia? Either of them? Nope. Do I need age by grip? Nope. Do I need this one? Yeah, I need sex by dementia group, both of them. So the three terms that are showing up in these three lines, just the main effect of gender, not the main effects of dementia, and then turning on each of the contrasts. So the main effect of dementia is for the none group. The main effect plus the interaction gets to be what it is for future. The main effect plus the current one, or interaction, gets to be what it is for current. Going the other way, this one, let's do just these two right here. This is spinning it the other way. This is the dementia group difference between none and future for each gender. And so here, the main effect of gender is gone. We need the none versus future main effect to be started off, and then we need to turn it on for women in the second case. Likewise, this one, none versus current in men is the first line. Turn it on for women in the second line. And then the last two lines are the ones that are not provided by the model but are implied. It's the simple effect differences in the non-reference group, future versus current. And you get the pattern of -1, 1, the same as we did when we had main effects. And because these are -1, 1, the interaction terms stay with it. So in this case, if we look at just this line right here, future current difference is given to us by this part. We take those values that we already gave and we multiply them by the value for gender for which we want the effect. In this case, because I want it for men, and men are 0, these interaction terms go to 0. In this case, because I want it for women, and women are 1, the pattern is the same as what it was for here. Okay. With me?
You mentioned the variables you didn't enter here is you treat control for them as constant.
They're treated as constant at, so up here, because age and grip are not in here, they're being held at their 0 values.
Oh, okay.
And so these would be considered adjusted means. Down here, though, they are being held at their 85 and 9 reference values, but it doesn't matter because the model doesn't say that these differences depend on age or grip. So it's like, if you look at the means on the y-axis, you know, they slide up or down as a function of age or grip, but the relative differences stay the same because they don't interact with age or grip. Good question. So far, all I've gotten are main effects. They're main effects for particular group combinations, but they're just main effects. I don't have anything that actually tells me about the interaction. What did you learn about interactions in ANOVA land? How do you talk about them? Nobody has a go-to? Or you don't remember? So I remember mine. It's still drilled in my head. Different differences. It's that these differences are different as a function of something else. So the next set of terms take each of these differences and compare them. So if I want to know, for instance, if the sex difference differs between none and future dementia, Say that again. Does the sex difference differ between none and future dementia? I take the second line and subtract the first. And that gets me down here. Conveniently, that is exactly what this interaction term is telling me. Does the sex difference differ between none and future? If I want to go the other way, if I wanted to talk about the none-future difference between men and women, does the effect of dementia differ by gender? If I take the second line and subtract the first, it's identical. So that is to say, I can talk about this interaction term of sex by dementia NF either way. It is either how the sex effect differs between dementia groups or how the dementia effect differs between genders. It's both. That's my interaction. So there are 3 possible distinct interactions implied by this model. If you look at the numbers here, the first 2 lines give you one of them. The second 2 lines give you the second. Those are the 2 that I have asked for specifically given my coding. The second one I can think of as how the sex difference differs between none and current, or how the none-current difference differs by gender. The third one is not going to show up anywhere in my output unless I ask for it, but it is still in the model. It's whether the sex effect differs between future and current, the 2 alternative groups, or whether that alternative group difference differs by gender. And that's the -1,1 coding to contrast between the non-reference groups that we've seen a few times now. So here is what we get. I have 2 tables printed here for you. The second table I typically skip, but I'm printing it here to make a point. The first table is the solution for fixed effects. This aligns directly with the betas in my equation. They're betas instead of gammas because we're in regression land, but it'll be the same when we get back to mixed models. The intercept beta 0, beta 1, 2, 3, 4, 5, 6, 7, 8. Each of these is testing one thing at a time. And so given that we are using denominator degrees of freedom, the ratio of estimate to standard error is being treated as a t. Look at the age effect here, for example, and the age, looks like I cut off the word age somehow. That's what happens when you paste in output. Let me look at this age effect and this one right here. Probability that t is greater than the absolute value, probability that f is greater. They match. They should. What's the relationship between t and f? Squared, yes. They match. They're telling you the same thing. Very comforting. That is true for every single term in this table, because it is not combining or marginalizing across anything, because you set up the coding and it doesn't understand how it would do that. F times numerator degrees of freedom is chi-squared. So I asked it to print both to make that point. The difference in the p-values, what's the difference between these 2 tables? What?
I mean, like, some of them are, like, slightly off.
Yeah, why are the p-values slightly different? Which one of them is using this denominator degrees of freedom? F. What's chi-square using for denominator degrees of freedom? Infinity. It doesn't have one. So I point this out because programs will differ in what they give you. If you're using a program that is using denominator degrees of freedom, you're going to get T's and F's. If you're using a program that does not, such as M+, such as default stata, you're going to get Z's and chi-squares. If you have enough people, it doesn't matter. What is enough? Like, I don't know, 20, 30-ish, right? I have to go back and look up at my T-tables from back in the day, but, you know, less than 541. So down here then is all of the output that I asked for with respect to the simple effects of sex, the group differences, the simple effects of dementia group, and the differences between those simple effects in terms of interactions. And I have stuck those differences up in the table here and included their p-values. So for instance, let's look at this number right here. The interaction contrast is 0.16. That tells me two different things. It tells me that the gender difference in the none group, which is, let's see, where's that at? 2.87. And the gender difference in the future group, which is 2.71, differ by 0.16. So if I look at these p-values up here, I can say, do men outperform women if they don't have dementia? Look at the means, look at this result. Do men outperform women if they don't have dementia? Are men higher than women if they don't have dementia? Yes. Are men higher than women if they're going to get dementia? No, not significantly. Now, look at the size of these two effects. They look kind of the same, don't they? Mm-hmm. And in fact, these two numbers, 2.8 and 2.7, are not different. That's the test of the interaction. So why do you think one is significant and the other one isn't? What else has to go into this story here besides just effect size?
Variance.
Variance. Keep going. Sample size. Yeah. In this particular sample, there's not very many people in the future group. So the standard error for that difference is much higher. So even though I want to be able to say there is a significant gender effect in one group and there's not a significant gender effect in the other, I can't say those gender effects are actually different. Now if I go the other way, let's talk about the dementia effect. The dementia effect between none and future in men is 6. The dementia effect in women between the same two groups is 5.9. Each of these numbers is significant. But is there a significantly bigger dementia effect in men than women? Nope. 6 and 5.9 are the same. And I can go through all of the other ones if you want, or you can say that you get it. Get it? Okay, so this 7.88 is either the difference of these two simple effects or those two simple effects. But to be able to actually answer the question of how dementia group interacts with gender, you have to be able to talk about these specific types of interaction contrasts. And this is the thing that they don't give you unless you code it yourself or know how to ask for it. Here are my F tests for those things. Now I want to show you what happens when you switch the coding so that sex is continuous, but you're letting SAS do the coding for group as categorical. And this is where you get two different answers in the same output. You ready? Do I have your attention? Isn't that scary? Two different p-values to answer the same question? It's not the same question. It just looks like it is. So I have dem group here. Gender is being treated as continuous. Same model. I've just changed the coding scheme. Same model, same R square. What shows up in terms of how you decompose the effects is going to differ as a function of the new coding scheme. So to your question, note the at statement. We are holding the covariates age and group at their 0 values as we did before, but I have to hold gender at something as well now. So I'm asking for 3 sets of marginal means for group. Actually, the first one is marginal because I'm using gender as 0.5. I'm marginalizing over gender. And the second is specific to men and specific to women. Now, let's look at this. Those two sets of results. Okay, I'm going to need some mathematicians in the house. Who wants to be my mathematician today? Yeah, it's always you, right?
That's my destiny.
Yeah, that's your destiny. Okay, so here's your quiz. What is 3.71 squared? I'll change it into an easier question. Is it 19?
I believe so. No.
No, I don't think so. I think it's somewhere between 9 and 16, if I had to guess, right? But closer to 16? It's not 19, though.
Yeah.
So how do I have sex MW as a line with this p-value and sex MW as a line with a different p-value? What looks like the answer changes to the same question. It's not the same question, and therefore it's not the same answer. In the top table, this is the coding scheme in which all of the contrasts are listed explicitly. These are therefore all simple main effects or interactions. So the lines that have the dots and the zeros, that denotes your reference group. It is now current, because that's the default for SAS. So what this minus 10 means for this sex effect, it is the gender difference for the reference group. This is the difference between men and women who currently have dementia. That's what this is. Minus 10. If I go back up to my table O means here, 17.1 minus 6 and some change. I'm rounding, but it's 10 to 11-ish, right? That's that one. So then if that's for the current group, what is this one? It ain't the current group, because 3.7 squared is not 19. Is it for the none group? The future group? Marginal. So for what kind of person is this the test of gender?
Non-existent?
Yeah, nobody. The average of somebody who doesn't have dementia, will have dementia, and already has it. And this is what it gives you by default. Tell me how that's helpful. What kind of person am I going to generalize that to? Dem group now, this is 2 degrees of freedom because this is lumping together the 2 contrasts up here. And sex by Dem group is lumping together these 2 contrasts. It could have been any of the 3 contrasts. Any 2 of the 3 would do it. Here are the least squares means. 27, 21, and 11 are how I got to the marginal means over here. The other ones are holding gender at 0 or 1, and then here are all the differences that we already found. Here's how I would get all of the simple effects if I didn't have group difference equals all. Difference equals all takes care of all of the middle ones. I have to ask for the ones for gender, and then the interaction contrasts are down here. The interaction contrasts are the ones that they don't give you, and that's what you would want. Okay. So who thinks this is like way too much typing? Me. Who would like to do less typing? Me. Okay. So let's make them both categorical, but let's make sure we know what we're asking for. Making them categorical lets them do all the coding. It's less typing. So they're both on the class statement now. We're still holding them constant at age 85 in group 9. Here's the table. Now we have the explicit reference group listed for gender as well as for dementia. Note the coding scheme. This is a popular source of confusion. In my variable, men are the 0 and women are the 1. In my model, who is the 0? Women. It's backwards. Remember, SAS takes the highest group, alphabetically or numerically, and makes it the reference. So if you put in a dummy variable into the class statement, the 1 is the new 0.
Isn't it always better to explicitly tell us which group is the reference?
If you try to override it and tell it which is the reference, then these, where is it? The contrasts that I'm going to show you in a minute, these get out of order relative to the data, and it becomes really confusing. So what I typically do is just make sure that whoever I want to be the reference is the highest number. So I would take my 0 and turn it into 2, and then it stays 0, if that makes sense. So here is what default ANOVA output would be. So here's my gender effect where the F value is 19. That's the average. That's the gender difference between averaged across dementia groups. Likewise, my dementia group effect is averaged across genders. And I have a gender by group 2 degree of freedom interaction with a p-value of 0.03. How do I explain that? I have a significant interaction such that there's nothing here that tells me what this means. All I know is that there are differences of differences that are different somewhere. That's all I know. And what sometimes people will do in this situation is reduce their model to just, say, 2 groups and do like a t-test or something to try and figure out which sets of groups are different. Don't ever do that. Do you know why? Because this term is based on variance that is averaged across all of the groups. And the variance that you would get from just 2 is not going to be that same number. So it's not actually a follow-up. How do I know where the differences are? I got to ask for them. This right here. Six numbers after the interaction term. There's 6 cell means. To know the order, it's based on whichever variable is listed on the class statement first. And if you add slash and the letter E after each of these lines, it will tell you which cells are getting the 0s and the 1s so that you can check your work. But this is how I would ask for the sex difference for different specific dementia groups. Sex difference is -1, 1. I then assign that to whichever dementia group I want it for. In this case, this is for none. Moving over 1 digit would be for future. Moving over again is for current. If I want to go the other way, if I want simple effects of dementia group, so this is none versus future, and I want it for men, I assign the -1 and 1 to whichever spot is for men. So I have the order written right here for you to refer back to. But here's the same dementia group difference for women, and then none versus current for men, and so forth. And if I want to know if any of these differences differ, it's again the same principle. I start with one of the lines and subtract the other, and you end up with this combination right here. This part is completely non-intuitive if you don't start by subtracting. Because what you end up doing is taking one of the differences and contrasting it with the other, but the second one has to be backwards. So if I go 0, let's see, this is the sex difference for none versus future. If I go -1 minus 0, that's -1. 1 minus 0 is 1. 0 minus 0 is 0. 0 minus a -1 is 1. 0 minus 1 is -1. 0 minus 0 is 0. So one of these lines gets me one difference, the other line gets me the other. The difference of the difference is right here. That's the interaction. And it's the same deal as before. There are 3 possible interactions here. And I've written the same interaction as answering 2 different questions because it does. So none of this is given to you by default, but you absolutely need it to be able to make sense of these patterns. The stuff that's given to you by default when you use this coding, none of this is actually useful, I would argue. It's marginalizing across groups, and the interaction doesn't tell you which groups are actually have different differences. Slice is another term that I want you to become acquainted with. That's how you ask for simple effects per. Slice means per. So in this line here, I'm asking for the group means, where slice equals dem group. That means I want the sex difference per dem group. If slice equals sex, I want the dementia difference per gender. So that gets you the simple effects. You still have to ask for the simple effect differences, but that's what all of these effect slices give you that we skipped over. Fun, huh? So, James, this is what you get to do, but with 13 of them, or 16.
Okay.
Okay?
Yeah.
Good? And actually, if you have pre-post for 16, you have 32 things written out here. Good times.
Yeah.
Yeah. Job security,
Lot of
people.
writing.
You learn how to do this, somebody will pay you.
Taxes don't sound as bad anymore.
I know, right? It's good. It's better than income tax, I think. So, all right. So we're going to do this next time with longitudinal data and 4 piles of variance. Yeah! You ready? Yeah! It's going to be awesome. So I will fix your quiz 5 right now. Let me know if you run into any more problems with homework or otherwise. Office hours start now. Hope to see you Thursday. Go out and enjoy the sunshine. All the undergrads are walking around in shorts.